Okay, in a previous video we have solved question number 1, that is on reverse Carnot cycle. Okay, and in this video we will solve question number 4. Okay, so what is the question number 4? Read it carefully first, and after that we will try to solve this. Okay, so the temperature limits of an ammonia refrigerating system are 25 degrees Celsius and 100 minus 10 degrees Celsius. Okay, remember this is a minus 10 degrees Celsius. If the gas is dry at the end of compression, calculate the coefficient of performance of the cycle, that is we have to calculate COP. Assuming no undercooling of the liquid ammonia, use following table for properties of ammonia. Okay, so here in the property table what is given? Temperature of the condenser, that is 25, and minus 10 is the temperature of the evaporator. Okay, so liquid heat, that is liquid heat means what? This is given HF. Okay, that is enthalpy, that is 298.9 and at minus 10 135.37. Okay, and latent heat kilojoule, that is latent heat means what? HFG is given. Okay, not HG is given here. Whatever questions we have solved in lecture, in that HF and HG was given, but here some different quantities are given here. Okay, and liquid entropy means nothing but what? SF is given. Okay, SF1 and SF2, right? So let us try to solve this example. So this is the question. Okay, I hope you are understood this question. Now let us try to solve this question. Now first of all, what we have to do, we have to draw this particular on PV and TS diagram. Okay, sorry, pH and TS diagram. So if you see here, it is given that at the end of the compression the gas is dry. What is meaning of this? That means at point number 2 there is a saturated vapor condition of the vapor, or of that particular refrigerant what is used, that is ammonia. Okay, so definitely what will happen here, this point number 1 will come in the liquid and vapor region, that is here. If you see in the diagram 1 to 2, point number 1 is in between, below the, or we can say that to the left of this particular saturated vapor line. Okay, and this 1 to 2 is isentropic compression, 2 to 3 is your condensation process, that is okay, and 3 to 4 is again expansion process, and 4 to 1 is evaporation process. So here evaporation temperature, that is given minus 10 degrees Celsius, and here 2 to 3, that is 25 degrees Celsius is the condenser temperature. Now if you see this diagram on the TS, here you can see clearly 1 to 2 is isentropic process. Okay, this is the straight line, and 2 to 3 is condensation, and 3 to 4 is your expansion process. Okay, and 4 to 1 is evaporation process. So I hope you got this diagram. Now what is given in the question, let us see this first. If you see in the TS diagram, T2 and T3 are same, so that's why it is a 25 degrees Celsius. Convert it into Kelvin, so it will be 298 Kelvin. If you see at the bottom, that is T1 and T4 are same, so minus 10 degrees Celsius, that is 263 Kelvin. Now what are the given quantities in the table? If you see, H3 and H4 are same. Okay, what is H3? H3 is nothing but your HF. Okay, so HF3 is given in the question at 25 degrees Celsius. So look at this, 25 degrees Celsius, at 25 degrees Celsius HF is 298.9. so here it is given 298.9 kilojoule per kg. Again HF1 is also given. Okay, what is HF1? So HF1, that means here actually here in the diagram it is the HFG. Okay, that is not given in the question. Here what is given? HF1 is given, that is minus 10 degrees Celsius. At the minus 10 degrees Celsius 135.37 is the your HF1 value. Okay, and what is value of HFG2? Okay, HFG2 is given in the question, that is latent heat. HFG2 1166.94 and HFG1 1297.68. Okay, similarly here if you see liquid entropy is given, that means HF 2, okay, or HF3 we can say that both are same. SF1, sorry, SF2, that is 1.1242, SF2 and SF1 both are same, okay, and this 0.5443 at minus 10 degrees Celsius is given, okay, that is how much, 0.544, okay, so it is SF1, okay, that is also given. Now these are the different quantities that are given in the question. Now let us assume that, look at this, at point 1 it is not perfectly saturated vapor, that's why some dryness fraction is considered at point 1. Let us assume that dryness fraction at point 1 is x, okay, let us assume that x is the dryness fraction at point 1. So we know that at point 1 we can calculate the entropy, that is S1 is equal to SF1 plus x1 into HFG1 upon T1. So this formula we have to remember very carefully. Look at this. S1 is equal to SF1 plus x1 into HFG1 upon T1. So by using this formula, we can calculate the value of S1. So SF1 is already given in the question. So that is 0.5443 plus x we have to calculate into HFG1 is also given in the question. So 1297.68 divided by T1 is 263. So this one you will get, so here S1 is equal to 0.5443 plus x will remain as it is 4.934 x1, or you can write x. This is equation number 1. Okay. Now let us see at point 2. So if you see at point, exactly at point 2, it is a saturated vapor line, right? So at this particular S2 point, we can write this as SF2 plus HF Hg2 upon T2, because S2 is directly not given in the table. That's why we have to calculate it. And this can be calculated with the help of this formula, SF2 plus, here remember, what is the difference between S1 and S2 formula? In S1, there was a dryness fraction. Okay, that's why we have taken their x, but here there is a saturated vapor line, and that's why their dryness fraction is always 1 on that line. That's why here we have not mentioned any x. Okay, so solve this. S2 is equal to 0.5443 plus 1166.94 upon 298. This is given in the table, and that is equal to 5.04. So you have got the value of S2, but remember, from the TS diagram it is clear that S2 and S1 are same. So whatever S2 we have just calculated, that is 5.04, it is nothing but your value of S1. So put this value of S1 in the equation number 1, and from that you will get the value of dryness fraction, that is 0.91. Okay. Now as soon as we get the value of this dryness fraction, now we can able to calculate the value of H1. Look at this. Now we can calculate the value of H1, okay, which is needed to calculate the value of COP. So how to calculate this value of H1? So again, we have to remember this formula for that. We know that enthalpy at point 1 is H1 is equal to HF1 plus X1 into HFG1. Okay. This formula is already we have discussed in the engineering thermodynamics. Okay. That is in semester 1. So it is assumed that you know this particular formulas. Okay. So HF1 is 135.37 plus x1 just we have calculated 0.91 into HFG1 is given 1297.68, and once you put these values in the calculator, you will get the value of H1 as 1316.26 kilojoule per kg. Okay. Now let us calculate the enthalpy at point 2. That is also not given in the question. So how to calculate this H2? H2 is nothing but HF2 plus HFG2. So just here x is absent. Otherwise this formula is similar to H1. So just put the values of HF2 298.9 plus 1166.94 is equal to 1465.84 kilojoule per kg. And once you get the values of H1 and H2, remaining things is very easy. That is COP is equal to what? H1 minus HF3. Here look at this, H1 minus H4 actually, but H1 minus H4, H4 is nothing but your H3, and H3 is nothing but your HF3. Okay, so just put the value of H1 minus HF3 upon H2 minus H1. Actually this is H2 here, this is H2. Okay, look at this now. So just put the values of H1 that we have already calculated here. HF3 is given, H2 we have calculated, and H1 we have just calculated, and from that we will get the value of COP as 6.8. Okay, so I hope you understand this question number 4, okay, from the question bank. So thank you very much. Now we will see the next question, difficult next question, in the next video. Okay.